Welcome back. Today, we're diving into a brand new explainer, taking you on an incredible journey from a single, impossible, scorching planet, all the way out to the humming fabric of the universe itself. If you love seeing the cosmic rulebook thrown out the window, you're in exactly the right place.
To hook your imagination right out of the gate, we've got to talk about TOI 561b. This exoplanet is twice as old as our Sun, whips around its host star in just 10.5 hours, and honestly, it completely defies everything we thought we knew about rocky worlds and how they hold on to their atmospheres in such extreme conditions.
See, based on our models, because it's so close to its star, TOI 561b should be a completely bare rock baking at nearly 4,900 degrees Fahrenheit. Any atmospheric gas should have been blasted into space a long time ago. But JWST data shows us something wild. It actually has a thick atmosphere, and it's running significantly cooler at around 3,200 degrees. How is that possible? Well, the atmosphere is actively distributing the heat. It's constantly exchanging gases with a churning, global magma ocean below it. It literally burps out gases it previously swallowed, acting exactly like a giant, wet lava ball. It is an absolute paradigm shift for planetary science.
So here is our roadmap for today's explainer. 1. Bizarre worlds and lava balls. 2. Asteroid Bennu and life's origins. 3. Comets from deep space. 4. Ancient black holes revealed. 5. The cosmic gravitational hum. And 6. Future tools of discovery.
Section 1. Bizarre worlds and lava balls. The James Webb Space Telescope is revealing a whole menagerie of planets that shouldn't even exist.
It's wild to look at the sheer diversity of these seemingly impossible systems. We're seeing everything from TOI 5205b, a massive Jupiter-sized world orbiting a tiny star, to a dead pulsar literally stretching a planet into a lemon shape, where a pure carbon atmosphere rains down actual diamonds. Not to mention rock-forming mineral clouds that just vanish every night on WASP 94ab. The chemistry here is completely off the charts.
What the heck is this? Seriously, that was the actual verbatim reaction from Carnegie astronomer Peter Gao when he saw the data for that lemon-shaped, diamond-raining planet. Astronomers are genuinely stunned right now. These newly analyzed worlds are completely rewriting the rulebooks of planetary formation, chemistry, and meteorology. We're quickly finding out that the universe is far more creative than our previous models ever allowed.
Which brings us to Section 2, Asteroid Bennu and life's origins. If solar systems can be this chemically diverse and bizarre, it begs a massive question. Where do the complex building blocks of life actually come from? Well, the magic number here turns out to be 14. Out of the 20 amino acids that life on Earth uses to make proteins, an astounding 14 were found in the pristine samples brought back from asteroid Bennu by the OSIRIS-REx spacecraft. We're talking about a 4.5 billion-year-old time capsule, and it is absolutely loaded with the precursors to biology.
Beyond just the amino acids, the Bennu samples handed us all 5 nucleobases needed for DNA and RNA, plus precursor volatiles like ammonia and formaldehyde. But honestly, the most incredible part? They found a complete set of evaporate salt minerals. That indicates Bennu's parent body hosted warm, alkaline groundwater for thousands of years. It wasn't just a cold, dead space rock. It was a hydrothermal broth, perfectly tuned for complex organic chemistry.
Moving on to Section 3. Comets from deep space. Because these life-building ingredients aren't just limited to our local asteroid belt. They are actively traveling through the void between stars. Take the comet 3I/Atlas, a confirmed visitor from way outside our solar system. In a brilliant feat of timing, spacecraft like Europa Clipper and JUICE coordinated their instruments to scan this comet as it passed by. They found highly elevated carbon and methane emissions, proving that this comet originated in a cold, carbon-rich molecular cloud. It confirms that the chemical building blocks necessary for life aren't unique to our neighborhood. They are scattered across different star systems all throughout the galaxy.
All right, Section 4, Ancient Black Holes Revealed. Let's zoom out from the microscopic building blocks of planets to the massive gravitational engines that shape entire galaxies, supermassive black holes.
We're so used to thinking of supermassive black holes as active quasars, violently tearing apart gas and outshining their host galaxies. But JWST just achieved a major milestone. It weighed a completely dormant black hole at 6 billion solar masses. It's totally silent, completely stripped of its infalling gas. This pretty much proves the theory that violent active quasar phases eventually heat up and blow away the surrounding star-forming gas,
shutting down the galaxy's growth and leaving the black hole on a silent, massive dormancy.
And man, this brings up an incredible chicken or egg question. Did these giant black holes form before their galaxies? JWST has spotted what astronomers are calling little red dots from the absolute dawn of the universe. These are massive black holes orbiting without a substantial host galaxy around them. This really points to something called a direct collapse black hole, where pristine primordial gas clouds collapsed wholesale into massive seeds, completely predating the stars and galaxies that would eventually surround them.
Section 5. The cosmic gravitational hum. When these ancient galaxies do finally form and eventually merge, their central supermassive black holes begin a dance we can actually hear echoing across the universe.
To detect this, scientists use what's called a pulsar timing array. Think of it as a galaxy-sized gravitational wave detector. By monitoring the highly precise millisecond flashes of rapidly rotating neutron stars scattered across the Milky Way, astronomers can detect the minute stretching and squeezing of space-time itself. And after 15 years of patiently listening, the Natograph collaboration finally found compelling evidence of a low-frequency gravitational wave background.
So here's the step-by-step of what we're actually hearing. First, galaxies merge, bringing their massive black holes together. Then, those black holes begin a tightening orbit over millions of years. Their in-spiral violently stretches and squeezes space-time. And because this has been happening for 13.8 billion years, all those overlapping waves from billions of massive mergers create a background cosmic hum. It is a literal rumble in the fabric of reality.
As Stephen Taylor from the Nanograph collaboration pointed out, this is opening an entirely new window on the gravitational wave universe. And this is incredibly exciting because, for a long time, there was a huge fear called the last parsec problem. The idea that these orbiting black holes might just stall out and never actually merge. But this background hum proves they do successfully merge, generating this incredible symphony of space-time.
Section 6. Future Tools of Discovery. With our universe proving to be more complex, chemically rich, and dynamic than ever, what instruments are we going to use next to unravel its secrets? While our roadmap of future discovery is pretty packed, in 2029, the OSIRIS-REx spacecraft will intercept the near-Earth asteroid Apophis. By 2031, the Psyche spacecraft will give us our first look at a stripped metallic planetary core. And on the horizon, we have the Nancy Grace Roman Space Telescope, which is gearing up to perform an absolutely massive all-sky near-infrared survey.
What makes the Roman telescope such a game-changer is its field of view, which is vastly larger than Hubble's, combined with a high-performance coronagraph. This instrument uses light waves to cancel each other out, a process called destructive interference, to basically block out blinding starlight. This allows us to directly image planets 1 billion times fainter than their stars. We're going to be able to find and characterize faint, rocky exoplanets sitting right inside the habitable zones of their solar systems.
Which brings us to one final thought. As our view of the universe expands from wet lava balls raining diamonds to the ancient hydrothermal broths of asteroids to the cosmic hum of supermassive black holes, what impossible phenomena will we discover next? We are just beginning to tune in to the true complexity of the cosmos, and the greatest discoveries, the ones that will completely upend our textbooks tomorrow, are absolutely still waiting in the dark. Thanks for learning with me today on this explainer. See you next time.